Okay, the last talk today is given by actually my postdoc, Eklavya Thareja, who's at University of South Florida with privilege around the state, and I'll let him.
So I changed the topic or the title of my talk a little bit. So what I'm going to talk about are tunable states and extended near extended defects in various topological systems, and I'm going to go into more detail about what systems we're talking about. So usually, as you probably know, topological materials are known for being robust against impurities. They provide some transport properties which are robust against impurities. And this has led to several proposals about applications in quantum computation and spintronics. And so what we are interested in is the ability to control the electronic states themselves. And there are two major properties that we're interested in controlling. First is spatial control. The second is spin texture control. And what we show in our work is that extended defect states host states which show both forms of control to various degrees. So we're interested in two classes of materials. First is topological insulators, and the second is Waltz-Lamé metals. So just as a reminder, you're probably familiar with topological insulators. They're insulating in the bulk, and on the surface, they have linearly dispersing states, which are known as 2D Dirac cones. And if you were to take a constant energy cut, you see spin momentum locking at the surface, Fermi surface. For Waltz-Lamé metals, these cones are 3D bulk cones, and they appear in pairs, with each pair having a chirality charge associated with it. And again, you have some sort of spin momentum locking if you take a constant energy cut. On the surfaces of Waltz-Lamé metals, you usually get these states called Fermi arcs, which connect the various nodes, pairs of nodes. And so these are the two major classes we're interested in, and we're going to look at extended defects. So, consider a topological insulator. Usually you would have some sort of step defect on top. So what we are interested in, if you could kind of deposit add atoms on that step defect, and let's say those add atoms are magnetic, you could basically try to look at what states you get near those step defects. So we do a continuum model, a minimal model, which basically is modeled by Dirac equation, which is a first order differential equation. So the wave functions are going to be discontinuous at those steps. So the first task is to find what the boundary condition is. So we do that. And the interesting thing that we see is that, so let's say that the add atoms provide an electrostatic and a magnetic potential. The dependence of the boundary condition on the electrostatic potential is a rotation matrix, while various components of magnetic potential have different effects. First effect is UX, let's say, which is basically the direction perpendicular to the defect. What you see is a spinor change that occurs at the boundary. UY, which is the direction along the defect, appears as a pure phase. So that turns out to be irrelevant. UZ will open a gap and requires a separate treatment. So we're going to focus on the electrostatic potential and the magnetic potential perpendicular to the step defect. So we look for states near the defect. We know the scattering states will live on the Dirac cone, but in addition to the scattering states, we find states which disperse along the defect, but are bound perpendicular to the defect, and they have dispersion shown in purple and green, while the gray dashed is the Dirac cone. What we see is by controlling the magnetic potential UX and the electrostatic potential U0, these states can basically have various velocities, different velocities. They have to be just smaller than the base Dirac velocity that's there in the bulk. And what we look at is we look at the spin resolved local. We calculate the spin resolved local density of states. which could be measured in a spin resolved STM. And so what we see is there are two major scenarios that could occur. If you were to take a constant energy cut, you will either encounter one branch or two branches of the bound states. If you encounter one branch at a constant energy cut, you have a peak around the defect in the local density of states, spin resolved local density of states. And away from the defect, you have Friedel oscillations. In the paper, we calculate how the Friedel oscillations will decay, etc. Similar oscillations and similar sort of peak exists for projection along Z. This was projection along X. But in addition, there is also a sign flip force Z, which comes from the mirror symmetries in the system. Now the question is, can you control any of this? And the answer to that comes from the constant phase that I talked about when we were discussing the boundary conditions. And that is dependent on this, the magnetic potential Uy. So you could use, by applying an in-plane magnetic field on the surface, you could use that to change the ratio of Uy to Ux, thus allowing for control of these states. In addition to the spin accumulation that would occur at this defect, we will also get some ground state charge currents, which basically comes from the fact that your charge current operator is just proportional to sigma for these spin momentum log states. And we calculate the two contributions, the bound state contribution and the scattering state contribution, and we add them up and we show that they will display a step-like behavior as you change the magnetic potential Ux. And that step basically depends on the chemical potential and the maximum of the valence band for the bulk, as well as it depends on the value of the electrostatic potential. So then, once we have these results for topological insulator step defect, we started looking at Waldsemer metals. And in Waldsemer metals, you can do something more interesting, where you can consider a planar defect. But as you go across that planar defect, the chirality of the nodes reverses. So does the spin texture associated with those nodes. So we started looking at a linearized model, and we asked the same question: are there states near the defect? What do they look like? Do they have an interesting behavior? So we wrote a simple model for that, which is part of the literature. So the first question we ask is, let's say you were to modify the potential by depositing some sort of interstitial layer at the defect, that would introduce an electrostatic, and if it's a magnetic interstitial layer, a magnetic potential. And so the first thing we ask is what kind of states you find. So if you have no potential, the states you find are shown, this dispersion is shown in black, while the wild nodes are in blue and red. So if you add an electrostatic potential, the dispersion sort of changes. And if you were to take a constant energy cut, you can kind of see what's happening. So if there was no electrostatic potential, your Fermi arcs go and connect the two wild nodes between the nodes and across the Berlin zone. And as you start increasing the electrostatic potential, you see there is a rotation that happens around each node. So that sort of comes from what the boundary matrix was telling us would really happen. So it can kind of be deduced from that. Then we introduce a magnetic potential into the system. And again, just like for topological insulators, there's one direction of magnetic potential that does not have any effect. It appears as a constant phase, while the other two directions have different effects. The direction Uy in this scenario changes the dispersion of the states, and you can kind of see what happens by taking a constant energy cut. And what's really happening is the two arcs, the two Fermi arcs are basically attracting each other. While if you do a similar calculation for the direction that is along the wild nodes, the magnetic potential direction along the wild nodes, what you basically get is there is no change in the shape of the Fermi arcs, but there is the distribution of the the distribution of the wave function shifts to one side or the other side of the. Then we look at the scattering states, which basically tell us what's happening to the electron as it goes through the planar defect. So for no potential, the maximum intertransmission probability appears on these positions in the momentum space. And that's basically coming from a matching of the spin texture on the two sides. When we introduce electrostatic potential, again, a rotation happens, which can be deduced from the boundary matrix. For UX, the position or the intensity of these maximas does not change. For UI, you see that they get pulled in one of the directions depending on the sign of UI. And that, because of spin momentum locking, indicates that there is some sort of spin filtering effect that's happening. For UZ, you see that the transmission maxima start getting suppressed. And so it sort of suppresses conductance. So what we did is we did a simple calculation using Landauer formula based on the transmission probabilities that we had. And what we find is if you have basically no potential, you get a factor of 2 by 3 with G naught. G naught is basically having a transparent barrier. And so you basically have reduction in the conductance when you start introducing UY and UZ, while U naught does not seem to change the conductance at all. So because from the previous, because from the transmission probability, we were expecting some sort of spin filtering. So we tried to calculate what the average spin of the transmitted electron is with respect to the incident electron. And we see that there's some spin polarization that happens for moderate values of UY compared to the hopping parameter. And so essentially, what we show in our work is depending on the spin momentum locking, it depends on what system, whether it's a topological insulator or Wildson metal, you get more or less universal behaviors for these potentials. Just the role of different potential mixes and matches depending on the kind of spin momentum locking you have. We think this is very interesting from the applications perspective because it sort of provides a way of thinking about what effects these potentials have on the spin momentum locked electrons in the form of the boundary matrix. So that's basically our work, and we're kind of we just submitted the second part of this. The first part of this work is already published in PRV. The second part of the work we just submitted, and the paper is going to come out on archive next week. Thank you. Thanks for your attention. Questions?
Are there any questions? Okay, so there's no questions. You can also ask them after. That concludes it for today. We can take this out.